Where is everybody? And is anybody out there? On a clear night, gazing up at the stars evokes a profound sense of wonder intermingled with our insignificance. Time and time again, humanity finds itself adrift within the boundless expanse of a universe that continues to elude our complete comprehension. As we cast our eyes toward the heavens, an enduring question lingers, seemingly just beyond our grasp. Amidst the countless billions of light-years of celestial tapestry above, could we be the sole bearers of life? In a cosmos teeming with possibilities, where life may flourish abundantly, a baffling silence persists. Why have we yet to encounter or hear from other intelligences? Two stark cases confront us. Either we stand alone in this vast cosmic theater, an isolation fraught with its implications, or we are not alone. A prospect that carries its own profound and at times disquieting implications. Many experts since have grappled with the same question. Considering the multitude of planets and stars in the Milky Way, why have we yet to hear from anyone? We call this problem the Fermi paradox, and there are several possible solutions, some more unnerving than others. In 1950, the Fermi paradox, attributed to the Italian-American physicist Enrico Fermi, first emerged during a casual lunchtime conversation with colleagues. Fermi posed a deceptively simple yet profoundly puzzling question in this frank moment. Where is everybody? Fermi grasped that any civilization with a modest amount of rocket technology and an immodest amount of imperial incentive could rapidly colonize the entire galaxy. Fermi's remarks spurred discussions and inquiries into the apparent absence of evidence for intelligent extraterrestrial life, despite the high probability that it might exist. This paradox has since become a central theme in the search for extraterrestrial intelligence, SETI. It continues to fuel scientific and philosophical debates about the potential existence of advanced civilizations beyond our own. When Fermi made this famous remark, the only planets scientists knew about were in our solar system. Nonetheless, there is another explanation that does not imply persistent loneliness and can be used to explain the Fermi paradox. What if life exists in space, but is only inanimate? The Great Filter theory was first proposed in the late 1990s by Robin Hanson, an economist at George Mason University. He said that our universe seems dead, suggesting it is tough for advanced, explosive, lasting life to arise. Hanson argued that there's something, or many things, out there that prevents intelligent, thriving life forms from surviving long enough on their home planet to expand to others meaningfully. Those threats included uncontrollable events like an asteroid hitting the Earth, and threats they believed could act as self-inflicted civilization killers. Those had nuclear war, another deadlier pandemic, out-of-control artificial intelligence, and climate change. As the study terms it, that sort of human dysfunction may snowball quickly into the Great Filter. He believes the more decentralized we are, the more likely that some of us will survive an Earth-ending event. If the Great Filter is behind us, it bodes well for humanity as a species. The universe may be ours for the taking. However, we may be doomed if the Great Filter still lies ahead. On the bright side, some have interpreted our apparent aloneness in the universe as a good sign, a blessing even, indicating we've safely made it through the bottleneck. Strange as it may seem, we may be the first species to have passed through the Great Filter. After all, someone has to be first. On the other hand, if we were to detect a signal from a super-advanced technological species that makes us look primitive, it might imply that the Great Filter still lies ahead. It's conceivable that advanced civilizations exist, but could they deliberately avoid contact or use communication methods beyond our current understanding? This could explain why we have not received any signals or detected their presence. Nikolai Kardashev, a Soviet and Russian astrophysicist, postulated a pioneer in how a civilization could grow by various stages. He designed a scale to measure a civilization's level of technological advancement based on the amount of energy it is capable of using. But what if we look at the possibility that the beings we are chasing to interact with are higher civilizations, and their messages in the form of signals would pass us by due to our underdeveloped technological advancements? This brings us to another potential avenue for searching for evidence of extraterrestrial intelligence, which involves detecting communications relying on gravitational waves. This concept finds its roots in Albert Einstein's theory of general relativity. The initial detection of these enigmatic waves occurred in 2016, marking a significant milestone. In the foreseeable future, We anticipate the establishment of gravitational wave observatories, which will enable us to visualize the presence of these ripples in the fabric of space-time. However, it's essential to recognize that generating detectable gravitational waves poses an immense energy challenge. The process is exceptionally demanding and far more complex than detecting neutrinos. It would necessitate capabilities akin to superheroes, enabling the deliberate collision of neutron stars and black holes. Despite the seemingly improbable nature of these explanations, they introduce innovative methods for the quest to uncover intelligent life. Since Frank Drake introduced his renowned equation, humanity has pursued evidence of intellectual extraterrestrial existence. Regrettably, our endeavors have been shadowed by Fermi's equally famous paradox. Nevertheless, considering the vastness of space exploration, we have merely scratched the universe's surface. To expect to discover evidence of intelligent life beyond Earth, we must persist in our pursuit. Armed with an ever-expanding knowledge base and increasingly advanced methodologies, we remain confident that if intellectual life exists somewhere in the cosmos, we will eventually make that remarkable discovery. Nevertheless, a lingering question persists. Will our signals ever reach someone or something in the great expanse of space? Or will they forever journey through the cold, uncharted void? The enormity of space is staggering, challenging our communication efforts across vast cosmic distances. A testament to this challenge can be observed in the behavior of stars, where despite their astronomical energy output, their brightness significantly diminishes with increasing distance. In 2003, philosopher Nick Bostrom introduced his renowned simulation theory, delving into the possibility that our reality might be nothing more than a meticulously crafted artificial simulation. Bostrom's theory contemplates a future society that achieves unparalleled technological prowess, enabling its patrons to create intricate artificial realms by utilizing immensely powerful computers. If this theory were indeed true, it would undeniably suggest that the Great Silence is merely an expected outcome, and the very beings we seek to encounter could be the architects of the simulation in which we find ourselves trapped. Furthermore, within the context of a simulation, there may be an opportunity to gain insights into the enigmatic constancy of the speed of light, a fundamental constant that governs the measurements of momentum in the universe. Even if we were to advance to a higher level of civilization, harnessing the power of various stars for cosmic exploration, it might remain impossible to surpass this constant, as it could be an intrinsic and unalterable feature of the simulated universe. However, it's important to emphasize that this idea remains speculative, and the challenge remains. How can we determine whether we exist within a simulation? The authenticity of our reality and Fermi's paradox, which ponders the existence of extraterrestrial civilizations, would continue to perplex us within this framework. Nature has its own rules, which means we must be prepared for everything in our search for alien life. There are numerous options, and knowing where to begin might take a lot of work. However, by investigating the conditions required for life, we may focus our search and raise our chances of discovering something genuinely exceptional. But what if the problem doesn't originate from us, but rather from the ecosystem of these alien beings themselves? These otherworldly species cannot survive on Earth due to a reversed bodily composition, making breathing oxygen impossible. But are carbon and water necessary for life? Indeed, what are the odds that visiting space aliens could simply step off their spacecraft and begin breathing our oxygen-rich atmosphere? Scientists usually assume alien life will use familiar terrestrial biochemistry and hope to find alien life by searching near water or supplying hydrocarbons. The assumption that alien life is likely to be based on carbon and water is traditional and plausible. While hydrogen is the most abundant element in the universe, followed by oxygen in third place, what indeed assures us that the closest available life would be based on these elements? Carbon and silicon share remarkable chemical similarities, as both can create bonds with up to 4 other atoms simultaneously. However, silicon stands out as one of the universe's most prevalent elements. For instance, it constitutes nearly 30% of Earth's crust mass, about 150 times more abundant than carbon in the same geological layer. Notably, life on Earth offers a compelling example of silicon utilization within biological structures, particularly in diatoms, a type of algae. These organisms consume over 6 billion metric tons of silicon annually in Earth's oceans, contributing to nearly 20% of the planet's oxygen production. Given these observations, it's reasonable to speculate that silicon might play a role in other celestial bodies' early stages of life. Silicon-based life forms could convert planetary atmospheres into oxygen, laying the groundwork for more advanced life to evolve. Silicon-based organisms thrive in environments too extreme for carbon-based counterparts, such as high-temperature or high-pressure settings. For example, silicon's superior thermal stability allows silicon-based life to endure scorching volcanic landscapes that carbon-based life could not withstand. However, it's essential to acknowledge the limitations of silicon as a primary building block for life. Silicon-based life would demand more energy to sustain metabolic processes and exhibit a reduced ability to adapt to environmental changes swiftly. Consequently, while silicon serves diverse biological functions on Earth, the likelihood of it serving as the dominant foundation for life here or elsewhere appears relatively low. Furthermore, some scientists propose that life could be founded on elements entirely distinct from carbon and silicon, utilizing substances like sulfur or phosphorus in their biological mechanisms. In these theoretical scenarios, life would possess vastly different chemical and physical properties than terrestrial life, necessitating entirely unique conditions for its thriving existence. The concept of self-replicating spacecraft, initially conceived by mathematician John von Neumann, has become a topic of interest among futurists, including physicist Michio Kaku, and has been explored in numerous hard science fiction novels and stories. These autonomous self-replicating probes are often referred to as von Neumann probes. They share specific characteristics with living organisms or viruses, as they can reproduce and increase in a manner reminiscent of biological life. The process begins with launching a von Neumann probe from its home star system to a neighboring one. These probes are equipped with interstellar propulsion systems and universal von Neumann replicators with human-level intelligence. In a new star system, the probe gathers raw materials, replicates itself, and dispatches copies, each venturing farther into the galaxy. The original investigation explores its current star system, conducts research, and sends findings home. These von Neumann probes also enable interstellar colonization by constructing life-sustaining environments with synthesized genomes. Robots built by the probe tend to the colony's embryonic individuals, allowing them to develop their civilization. Versatile probes can be reprogrammed remotely, enhancing technological advancements for future inquiries. The exploration and colonization speed hinges on probe transit times, replication speed, and strategy. While this method may span generations and require considerable time, it represents an idealistic and dedicated approach to the search for alien life. Ultimately, it could provide a conclusive answer to whether we are truly alone in the universe or not. One of the most mind-blowing facts in our existence is that space itself, the very fabric of the universe itself, doesn't remain the same. Masses curve and distort it. Groups in motion change their nature. Ripples flow through the cosmos at the speed of light. Space and time were not separate, immutable properties of the universe, but were linked into a single entity known as space-time. In 1929, Edwin Hubble made a groundbreaking discovery that provided the first observational evidence for the finite age of the universe. Using his time's most advanced telescope, Hubble observed a phenomenon that would change our understanding of the cosmos. He observed that galaxies farther from us appeared to be receding faster, indicating that the universe was uniformly expanding in all directions. This remarkable revelation leads to intriguing possibilities. It suggests that we reside in a remote universe region, separated by vast cosmic distances from other intelligent beings. Imagine the universe as a vast expanse, like an enormous cube. Within it, each potential intelligent civilization is isolated by cosmic gulfs. As the Great Filter hypothesis proposed, this cosmic separation has played a role in the apparent absence of other advanced life forms. It raises the thought-provoking notion that humans might be the sole surviving sentient species in existence. In such a scenario, our concerns about extraterrestrial contact might be unwarranted. However, the concept of encountering otherworldly beings is undeniably fascinating, albeit tinged with trepidation. We do not know their intentions, whether they would be benevolent or harbor hostile intentions, such as subjugating Earth's governments for colonization or using us as subjects in a cosmic research experiment. Alternatively, the simulation theory posits that we might already be in contact with such beings, trapped within their constructed simulation. This idea adds another layer of complexity to the search for extraterrestrial life. Yet, should these extraterrestrial beings exist, a crucial question arises. Can we advance technologically without self-destruction? Our world presently lacks unity, a vital foundation for our species' survival in the event of contact. However, unity and resilience could serve as formidable assets if we encounter advanced civilizations, even if our technological progress lags behind. Then again, the universe is filled with ETIs that are powered by the same mix of awe and fear as we are. Like us, perhaps their inherent curiosity and desire to answer the burning question, "Are we alone?" is enough to squash their fears. Or maybe they have already infiltrated our planet and secretly plan on dominating us from the inside out. Exploring the universe's origins, especially the moments preceding the Big Bang, is another avenue to unravel the mysteries of our cosmic silence. While this endeavor may sound speculative, it represents a quest to understand the very genesis of our universe from its inception. If you want to understand what happened right before the Big Bang, you can watch my video about it. Well, that's it for the video. If you enjoyed the video, like and subscribe to the channel, and I'll catch you later.